There are worlds that arrive in the imagination with a kind of noise around them, and others that arrive more quietly, with dust on the boots and long shadows at the edge of the light. Mars is one of those quieter worlds, at least once the first impression passes. It is not only the red dot in the sky, not only the old symbol of war, not only the place where stories so often send their pioneers and their outposts. In the careful language of science, Mars is something more specific and somehow more interesting. It is a rocky planet that seems to preserve its history in broad, patient layers. A world that was not kind, exactly, but may once have been less hostile than it is now. It's a planet with dry river valleys, ancient lake basins, gigantic volcanoes, a canyon system of absurd scale, a thin atmosphere, a lost magnetic shield, and a long record of change written into stone. And tonight, we will follow that record gently, one calm detail at a time. Welcome in, I'm Madeline Rowe, and tonight we're going to take a long, relaxing journey through the science of Mars. Through its thin atmosphere, ancient river valleys, giant volcanoes, lost magnetic field, wandering dust, and the still open question of whether it may once have been habitable. And if you like these quiet, research-backed episodes, please subscribe. It really helps the channel, and there'll be another case file for you soon. Back in my office, it is quiet enough that the room feels a little otherworldly. The lamp on the desk throws a warm pool of light, but beyond it, everything fades quickly into cooler shadow. The way warmth on a planet distant from the sun seems to exist only in thin local patches before the cold takes over again. Papers sit in low drifts at the edge of the desk, reddish in the lamplight, like a landscape shaped less by water than by wind and time. By the window, the glass reflects only part of the room and keeps the rest hidden, and on the folder in front of me, the label is simple. Mars. Not a slogan, not a promise, just a place name and a thick file of questions. Mars is the fourth planet from the Sun, smaller than Earth, colder than Earth, and wrapped in an atmosphere so thin that the phrase atmosphere can almost feel generous. It is often described plainly as a dusty, cold desert world with a very thin atmosphere, and that really is the right place to begin. If you stood on Mars, the sky would not look like ours. It would often appear butterscotch or salmon-coloured with suspended dust, and the air would do very little to hold in heat. Yet Mars is not static. It has seasons, it has polar caps, it has weather. Dust can rise in storms that grow from local events into planet-spanning veils. Frost forms, carbon dioxide freezes seasonally at the poles. The world can seem dead at first glance, but it is active in the slow, dry, atmospheric way of a planet still responding to sunlight, slope, ice, and wind. A day on Mars, a sol, lasts about 24.6 hours, which is close enough to an Earth day to feel almost familiar. A year, though, is much longer, 687 Earth days, or nearly 2 of our years. The axial tilt is broadly Earth-like as well, which is why Mars gets seasons instead of living in one permanent climatic mood. But those seasons are stretched and uneven because Mars follows a more elliptical path around the Sun. So Mars offers this strange mixture of the familiar and the alien. The clock is almost recognizable. The calendar is not. Noon exists, sunrise exists, winter exists, but all of them feel translated into a harsher dialect. Even the 2 tiny moons, Phobos and Deimos, look less like proper round moons than captured rubble, irregular and battered, hanging around a planet that seems always to preserve the marks of impacts rather than smoothing them away. Mars also changes the feel of motion itself. Gravity at the surface is only a little more than a third of Earth's, which means a body there would weigh less, fall differently, and move with a strange mix of ease and caution. A thrown stone would arc farther, dust would hang and settle in unfamiliar ways. The atmosphere, meanwhile, is so thin that a person could not rely on it for pressure or warmth or breath. The result is a world that is neither entirely foreign nor comfortably familiar. It borrows enough from Earth to keep the mind comparing the two, then interrupts the comparison at every turn. The sunlight is weaker, the air is thinner, the cold is sharper. The horizon, with Mars's smaller size, can feel a little nearer. It is the sort of planet where your instincts would almost work, and almost is not the same as enough. Inside, Mars appears to be layered much as Earth is layered, with crust, mantle, and core. But the history of those layers unfolded differently. Mars is a smaller planet, and smaller worlds generally lose internal heat faster. That matters because heat drives a great deal of planetary drama. It helps sustain volcanism, helps power magnetic dynamos, helps shape tectonic behavior, and influences how long a planet remains geologically vigorous. Mars clearly had enough early heat to differentiate, to erupt on astonishing scales, and to generate a magnetic field. But over time, the planet cooled, the dynamo shut down, and the story shifted. Mars did not stop being interesting. It simply changed from a more internally vigorous world into one whose great revelations often survive as preserved records rather than ongoing upheaval. The surface itself is one of the great reasons Mars matters. Mars is about half Earth's diameter, yet because Earth's oceans cover so much of our planet, Mars has nearly the same surface area as Earth's dry land. And spread across that land are extremes. Valles Marineris is a canyon system more than 3,000 miles long. Olympus Mons rises more than 25 miles from base to summit, making it the largest volcano in the solar system. The southern highlands are old, cratered, and battered looking. The northern lowlands are lower, smoother in many places, and part of one of the planet's deepest mysteries, why Mars is split so dramatically between north and south in the first place. Just to list these features is to risk turning Mars into a set of superlatives, but the important thing is not that they are large, it is that they are legible. Mars keeps old landforms around long enough for us to study them. It does not erase and recycle its face the way Earth so often does. That last point is the quiet centre of the whole story. Earth is an active, renewing world. Plate tectonics shuffles crust, mountains rise and wear down, oceans open and close, and the oldest records are often buried, melted, folded, or destroyed. Mars seems to have spent much of its history in a different tectonic regime, without Earth-style plate tectonics constantly reworking the crust. That means ancient terrains remained at the surface. Old impacts remained visible. Ancient volcanic provinces remained broad and readable. Sedimentary clues that would have been erased on Earth could remain on Mars for billions of years. Mars may preserve a near pristine record of early rocky planet environments, not because it was more active than Earth, but because in some crucial ways it was less efficient at forgetting. That is why Mars is not simply a target in the search for life, though it is certainly that as well. It is also a kind of planetary archive. Mars exploration is often organised around four broad goals: determine whether life ever arose on Mars, characterize the climate of Mars, characterize the geology of Mars, and prepare for human exploration. Those goals fit together better than they might first appear. To ask whether life ever arose, you need to understand whether water endured, whether energy sources existed, whether the atmosphere and climate allowed habitable conditions, and whether the rocks where signs of life might be preserved are still accessible today. To prepare for eventual human exploration, you need to understand the same planet in a different register: dust, radiation, soil chemistry, ice, weather, terrain. Mars is one file with several tabs, not several unrelated cases. Mars also comes with its own geological clock. On Earth, we date time with a deep library of rocks, fossils, and radiometric clocks. On Mars, where samples are rare and field geology is performed by rovers and orbiters, broad eras are often defined by crater counts and the relative ages of surfaces. The old names are beautiful in a dry, formal way: Noachian, Hesperian, Amazonian. The Noachian is the ancient, heavily cratered early Mars, the age of the oldest preserved surfaces, and the strongest evidence for abundant liquid water. The Hesperian is a transitional era, when volcanism remained important and catastrophic floods carved enormous channels. But the older style of widespread fluvial activity seems to have diminished. The Amazonian, which continues to the present, is the long cold aftermath, a Mars dominated by wind, ice-related processes, local volcanism, and the slow working over of an already ancient surface. The boundaries are not absolutely fixed, but the framework is useful because it turns Mars from a postcard into a history. Before we go deeper into that history, it helps to remember that our own understanding of Mars also has a history. The Mars we talk about now is not the Mars scientists first saw. Early telescopic Mars was a small disk with shifting dark markings, bright polar caps, and just enough ambiguity to encourage grand mistakes. Later, spacecraft ended some fantasies and opened better ones. Mariner flybys in the 1960s showed a cratered, moon-like surface in the places they passed, which for a moment made Mars seem simpler and deader than many had hoped. Then Mariner 9 arrived in orbit in 1971 and found a planet wrapped in dust. When the storm slowly cleared, it revealed volcanoes, canyons, channels, and a world far more geologically varied than the early flybys had suggested. Mars became both drier and more interesting at once. Viking added another layer in the 1970s. The orbiters mapped the planet in growing detail, and the landers sent back images of rocky plains under pinkish skies, along with weather data, soil measurements, and the famous life detection experiments whose results have been argued over for decades. The Viking biology experiments never delivered a clean, enduring consensus that life had been found. In a way, that uncertainty set the tone for modern Mars science. Mars does not usually say yes or no in a simple voice. It presents chemistry, context, ambiguity, and the need for better questions. Viking helped teach researchers that the most productive route forward might not be a dramatic one-step test for life, but a longer program of understanding habitability, geology, mineralogy, and preservation environments. Later missions turned that long program into method. Pathfinder and its small rover Sojourner proved that mobile surface exploration could work. Spirit and Opportunity transformed Mars from a place of single landing spots into a world that could be investigated by field geologists on wheels. Phoenix dug into icy soil near the North Polar region. Curiosity shifted the focus towards sustained habitability in Gale Crater. Perseverance sharpened the search for biosignatures, and began caching samples for possible return. Meanwhile, orbiters kept adding context from above. So when we talk about Mars tonight, we are really talking about a planet assembled from decades of patient correction, a world understood by repeatedly returning to it with better instruments, better maps, and more disciplined expectations. If you picture the earliest preserved Mars, picture not yet the tidy red desert, but a rougher, darker, more heavily battered world. The Noachian begins close to the era of intense bombardment in the inner solar system. Huge impacts struck Mars and left basins whose scars still structure the planet's geography. At the same time, Mars was differentiating internally, building crust, and likely operating a magnetic dynamo that magnetized parts of the ancient crust. Today, Mars has no global magnetic field, but highly magnetized regions in the southern hemisphere preserve the memory of one that existed about 4 billion years ago. That matters because magnetic fields help shield atmospheres from direct interaction with the solar wind, and because a more protected surface changes the story of radiation, climate, and habitability. In other words, early Mars may not have looked like a paradise, but it may have been less exposed and less stripped than the Mars of today. In that older Mars, water becomes unavoidable, not because every scientist agrees on a warm blue ocean version of the planet, they do not, but because the surface keeps pointing back to liquid water in one form or another. Ancient valley networks branch across old terrains with a geometry that, to many geologists, looks more consistent with persistent runoff than with a world shaped only by rare trickles or isolated outbursts. There are deltas, lake basins, layered sediments, altered minerals, and rock chemistries that imply water-rock interaction. There are clays in Noachian terrains that suggest extended alteration. There are lake deposits and channels that indicate water moved sediment from one place to another over time, not merely in a single dramatic event. Exactly how much water, how often, and under what temperature regime remain debated. The debate does not erase the valleys. One of the gentler ways to think about ancient Mars is not as Earth's twin, but as a world where pieces of the hydrologic cycle may have worked intermittently, locally, and at different intensities across time. Some models favour a generally cold Mars with episodic warming. Some landforms suggest snowmelt may have been more important than steady rainfall. Some scientists still argue for intervals with thicker atmosphere and more clement conditions. What matters for a sleepier, slower understanding is that Mars does not seem to reduce to one simple climate picture. Instead, the record hints at transitions, regional differences, and changing modes of water activity. Rivers may not have flowed everywhere, always. Lakes may have filled and shrunk. Floods may have surged catastrophically through some regions long after gentler valley formation had waned elsewhere. Mars may have hosted multiple watery stories, not one. That complexity is part of why certain minerals matter so much. Clay minerals usually suggest comparatively neutral or moderate water chemistry and prolonged interaction between rock and liquid water. Sulfates can point toward more acidic or evaporative conditions. Carbonates, where found, raise their own questions about atmospheric carbon dioxide, local chemistry, and how much of the planet's climate history became locked into stone rather than remaining in the air. A listener does not need to memorize a whole mineral catalogue to feel the point. The rocks are not merely rocks, they are records of environments. A clay-rich outcrop is not only a patch of altered ground, it is an argument, preserved in mineral form, that water stayed, reacted, and changed what it touched. The classic Noachian evidence tends to feel almost terrestrial when described plainly. Valley networks imply drainage over landscapes. Deltas imply sediment entering standing bodies of water. Clay minerals imply chemistry that took time and liquid water to develop. Jezero Crater, where Perseverance now works, was chosen in large part because scientists interpret it as an ancient lake basin with a river delta. Gale Crater, where Curiosity landed, offered layered sediments that could preserve a long record of changing environments. These are not random scenic choices. They are archival choices. If life ever had a chance on Mars, sedimentary environments where water once stood, moved, deposited, and altered minerals are some of the best places to look for its traces. Not for moving organisms, not for waving forests, but for chemistry, textures, structures, and preserved signatures in rock. There's also the question of whether early Mars had oceans, especially in the northern lowlands. This is where the science becomes especially careful. Some proposed shorelines, sedimentary deposits, open basin deltas, and buried low-density materials have been interpreted as evidence for large bodies of water, perhaps even an ocean in the northern plains. Other analyses challenge those interpretations or argue the evidence is not yet decisive. It is one of those subjects where Mars invites the imagination forward, and the best science patiently pulls it back by the sleeve. There may have been long-lived bodies of water in the north. There may instead have been more episodic, regionally variable water bodies that mimic some ocean-like signatures without requiring a stable global sea. The right tone for this question is interest without insistence. The same caution belongs in any conversation about habitability. Habitability is not life. It means conditions capable of supporting life as we know it. A solvent such as water, temperatures and pressures within some workable range, energy sources, and the necessary chemical ingredients. By that standard, parts of ancient Mars may well have been habitable. Evidence points to water, carbon, chemical energy sources, relevant minerals, and analogies with extreme environments on Earth. Hydrothermal systems are especially interesting here. Impact craters can fracture crust, move heat, and generate hydrothermal circulation. Water interacting with heated rocks can create chemical gradients that on Earth support microbial ecosystems and, in some origin of life scenarios, may help drive the chemistry of life's beginnings. Mars, with its impacts, volcanism, groundwater, and ancient magnetic field, may have offered some of those ingredients. But may have is doing honest work in that sentence. That careful distinction is part of what makes Mars science so absorbing. The clues do not line up into one dramatic declaration. Instead, they keep assembling a plausible setting. Ancient Mars appears to have had water in some persistent or recurring forms. It appears to have had a thicker atmosphere than it does now. It appears to have hosted hydrothermal and sedimentary environments that, on Earth, can be habitable. It appears to have possessed a magnetic field early on. It almost certainly had abundant volcanic and impact-driven heat sources. And yet, the question remains beautifully, stubbornly open. Did life ever actually arise there? That is one reason Mars has remained such a serious scientific target. The evidence is strong enough to make the question rigorous and incomplete enough to keep it honest. In some reviews, Mars is described as a time machine to pre-Cambrian Earth, and that phrase earns its keep. Not because Mars was simply early Earth in redder clothing, it was not, but because Mars may preserve a record of rocky planet processes from an age of solar system history that Earth has largely overwritten. On Mars, you can study volcanism, sediment transport, impact modification, weathering, hydrothermal possibilities, and ancient crust without the additional complications of plate tectonics and a biosphere that later transformed everything. Mars is simpler in some ways, and therefore clearer. It lets us ask what a planet looks like before continuous recycling and long biological overprinting blur the first chapters. It is not a perfect analogue. It is a surviving one. If Noachian Mars is the era of the strongest watery hints, the Hesperian feels like the era of transition. The impact rate dropped relative to the earlier age. Volcanism remained important, perhaps peaking in some estimates. Broad volcanic plains spread across major regions. Sulfate deposits appear prominently in some places, implying environmental chemistry different from the clay-rich story of older terrains. Large outflow channels carved through the landscape, sometimes on astonishing scales, suggesting catastrophic releases of water from subsurface reservoirs or ice-rich ground. In this era, Mars may have moved farther away from the conditions that made valley networks and widespread alteration more common, and toward the colder, drier regime that would later dominate. But it was not a simple switch being flipped. It was a planet rebalancing itself. Volcanism is part of that rebalancing, and on Mars, it rarely knows moderation. The Tharsis region alone is one of the most extraordinary volcanic provinces in the solar system, thousands of kilometers across and built from immense volumes of lava. Olympus Mons, Ascraeus Mons, Pavonis Mons, Arsia Mons, Elysium Mons. Even the names sound like entries in a ledger of excess. One reason Mars hosts volcanoes so much larger than Earth's is that the crust does not move the way Earth's does. On Earth, a hotspot can feed volcanoes on a moving plate, producing chains. On Mars, in the absence of that same plate motion, lava can keep piling up in the same broad region. The result is the kind of scale that seems almost theoretical until you remember the topography is real. The volcanic style itself also seems to have changed over time. Martian geology points to widespread volcanism in the late Noachian and Hesperian, then a decline in intensity and a progressive confinement of activity to certain provinces during the Amazonian. There may also have been a shift from more explosive styles earlier on toward more dominantly effusive volcanism later, possibly as the crust dried out. That matters because volcanism is never just about surface shape. Volcanoes move gases from the interior to the atmosphere. They build terrain, create fractures, alter local heat flow, and interact with any available water or ice. A volcano can be a climate actor, a geological architect, and, under the right conditions, a potential engine for habitable chemistry. On Mars, those roles may have overlapped in complicated ways across billions of years. Then there is Valles Marineris, the vast canyon system that seems almost too large to process properly. It is not simply a Martian Grand Canyon, because its origin is not just fluvial incision in the earthly sense. It is strongly tied to tectonic stretching, subsidence, collapse, and the stresses associated with the rise of Tharsis. Later erosion, landslides, sedimentation, and perhaps local water-related processes complicated that initial framework. So Valles Marineris is not merely a canyon, it is a structural wound, a region where the crust registered strain on a continental scale. To look at it from orbit is to see Mars not as a flat red marble, but as a planet that could crack. The Hesperian is also where catastrophic water comes roaring back into the story. Even if widespread earlier valley formation was diminishing, some of the most dramatic channels on Mars appear to record sudden releases of enormous volumes of water. The timescales for such floods may have been short, perhaps days or weeks in some cases, which is why they do not automatically imply a stable, warm climate. A flood is not the same thing as a long, wet world, but the channels matter because they show Mars still had access to substantial water, likely in subsurface storage, ice, or pressurized systems. The planet may have been drying on the surface while still hiding large reserves below. That hidden water Mars is in some ways more intriguing than the postcard version, because it suggests a world whose liveliest interactions were shifting downward and inward. By the time we reach the Amazonian, Mars has entered its long, austere phase. This is the Mars most visually familiar to us: cold, dry, windy, thin-aired, with ice at the poles and in the subsurface, with dust moving across plains and dunes, with meteorites striking a surface not well protected by thick air. Yet even this modern Mars is not inert. The Amazonian includes resurfacing by wind, local volcanism, ice-related landforms, frost, gullies, dust devil tracks, seasonal changes, and the slow rearrangement of sediments under a weak but persistent atmosphere. Some volcanic activity may have continued into geologically recent times, perhaps even within the last few tens of millions of years in some regions. On a human scale, that sounds ancient. On a planetary one, it is recent enough to keep the file open. Wind becomes especially important in this later Mars. Without a thick atmosphere, it might seem surprising that wind could matter much at all, and yet over long times, it matters immensely. Dust is lifted, sorted, transported, and redeposited. Sand dunes migrate. Fine coatings alter thermal properties and colour. Dust storms can rise locally or grow until they cloak the planet. The atmosphere today is regulated by seasonal carbon dioxide ice caps, moving dust, and exchanges of water vapour between surface and air. Thin does not mean trivial. It only means every effect must be understood on its own sparse terms. Martian weather also has a way of being understated until suddenly it is not. Local winds move through crater rims and down slopes. Dust devils trace dark or bright lines across the ground. Frost appears in the cold hours and retreats. Then in some years, dust storms grow broader and broader until much of the planet disappears beneath suspended fine particles. These events matter not only because they change what Mars looks like from orbit, but because dust influences temperature, circulation, solar power, and visibility. On a world already defined by thin margins, dust can become a planet-scale modifier. It can dim the surface, redistribute heat, and temporarily make the familiar planet look hidden from itself. The polar regions deserve their own hush. Mars has caps of water ice and seasonal carbon dioxide frost, and the layered terrains there preserve a climate archive of sorts. Those layered deposits are a useful reminder that climate is not only something that happens in the air, it is something stored in ice, in dust, in repeated patterns of accumulation and retreat. Orbital changes over long periods alter how sunlight is distributed across the planet, and the poles respond. Material builds up. Material is removed. The surface records a rhythm too slow for any one observer to watch directly, but not too slow for geology to remember. The polar caps are not side characters. They are one of the places where the recent planet keeps telling on itself. Ice on Mars is not confined to the poles, either. Orbital measurements and radar studies have revealed widespread water ice in the subsurface at high latitudes, and in some places startlingly near the surface. There are landforms that suggest buried ice, past glaciation, debris-covered ice masses, and cold climate movement of ground materials. This matters scientifically because it expands the story of water beyond the early warm or wet debate. Even a cold Mars can still be a water world in the sense that large reservoirs remain locked away as ice. It also matters practically because any future human presence would care very much where accessible water ice sits, how pure it is, and what the surrounding terrain demands in exchange for using it. All of this brings us back to the atmosphere. Because Mars today is defined by what its atmosphere is not. It is not thick. It is not warm enough. It is not protective in the way Earth's is. The atmosphere is made mostly of carbon dioxide, with smaller amounts of nitrogen and argon. It offers relatively little shielding from impacts and allows heat to escape easily. At the equator at noon, conditions can be oddly split by height. Warmer at your feet, freezing at your head. Liquid water is unstable on the open surface for long. Ultraviolet radiation is a serious issue. Reactive chemistry in the soil can break down organics. If early Mars was more hospitable, something fundamental changed, and one of the great tasks of modern Mars science is figuring out how that change unfolded. This is where MAVEN enters the story with quiet importance. MAVEN is the Mars Atmosphere and Volatile Evolution mission, and its purpose is to understand the upper atmosphere and the processes by which atmospheric material escapes to space. In other words, MAVEN is not studying atmosphere as scenery, it is studying atmosphere as attrition. What was lost, how it was lost, how the solar wind interacted with an unshielded planet, and how that loss affected climate, water stability, and habitability. A planet can die by subtraction, and MAVEN studies the subtraction. The loss of the global magnetic field matters here too. A magnetic shield is not an absolute protection, but it changes how a planet interacts with the solar wind. Mars once had one. Now it has only regional crustal magnetism. Once the dynamo shut down, the upper atmosphere would have become more vulnerable to erosion by solar activity. Over immense timescales, that erosion helps explain how a world that once supported rivers, lakes, and floods could become the cold desert we see now. It is a beautiful example of planetary science at its best. Not a single dramatic image, but a chain of physical processes connecting invisible escape in the upper atmosphere to ancient water on the ground below. There is even a peculiar beauty in the remnants of that magnetism. Mars does not produce a global auroral curtain like Earth's, but it can host localized auroral phenomena linked to crustal magnetic fields and solar activity. The planet carries the broken memory of its old shield in patches, as if the magnetic history were no longer a roof over the whole house, but a few surviving walls. That image is not scientific language, of course, but it helps capture something real. Mars lost a global protection and kept regional traces. Its story is often like that. Not total erasure, not full preservation, but partial memory. And yet we should not imagine the atmosphere as simply vanishing in one clean event. The timing and pace of atmospheric loss remain imperfectly constrained. Mars likely began with a thicker carbon dioxide atmosphere in the Noachian. Atmospheric loss proceeded, but alongside it there were exchanges among air, ice, rock, and possibly subsurface reservoirs. Water did not merely disappear. Some froze, some may have been trapped underground, some was lost to space after being broken apart, and some perhaps remained transiently available in brines or localized settings. Likewise, carbon dioxide moved among atmosphere, ice caps, mineral phases, and seasonal cycles. Mars is not just the story of loss. It is the story of redistribution under colder and thinner conditions. Present-day liquid water must also be handled with that same restraint. Briny streaks, recurring slope features, and chemically favourable micro-environments have all drawn attention, but the safe way to include them in the story is as possibilities and limited processes, not as evidence for stable open water today. The modern Martian surface is extremely challenging for persistent liquid water. If habitable environments exist today, many scientists suspect the best candidates would be protected subsurface niches not sunlit puddles sitting peacefully in craters. Modern Mars is probably least misleading when described as a place where water still matters profoundly, but mostly in frozen, hidden, or chemically constrained ways. If Mars is an archive, the spacecraft are its archivists. The modern picture of Mars exists because orbiters and rovers work together, each doing what the others cannot. Orbiters see context, global patterns, mineral distributions, topography, subsurface hints, weather, and relay geometry. Rovers see grain size, chemistry, rock texture, bedding, and the patient details of a single place lived in day after day. The rovers do not spend all their effort shouting directly at Earth. Instead, they pass their data upward to orbiters, which pass it home. That detail is so infrastructural, it almost disappears, but it deserves a moment. There is an invisible bridge around Mars that makes the visible exploration possible. Mars Odyssey is one of the veterans of that bridge. It helped create global maps of the chemical elements and minerals that make up the Martian surface and became one of the longest-lived orbital missions at another planet. Odyssey has studied clouds, frost, and surface composition and helped make future landing sites safer. There is something dignified about a mission like that, not as glamorous as a touchdown, perhaps, but foundational. Mapping elemental and mineral patterns at global scale turns the planet from scenery into a geological document. It lets scientists ask where ice is likely buried, where altered minerals sit, where volcanic materials spread, and how regional stories connect into one global one. Mars Reconnaissance Orbiter, or MRO, is another key investigator. Its cameras and spectrometers have provided extraordinary detail about the surface, subsurface, and atmosphere. HiRISE can resolve remarkably small features from orbit. CRISM searches for minerals formed in the presence of water. SHARAD probes the shallow subsurface for signs of underground ice and layered structure. Together, these instruments do something powerful. They connect shape, chemistry, and hidden structure. A valley can be imaged sharply, mineralogically interpreted, and contextually placed in a larger landscape. Mars becomes not only visible, but legible. There is also a practical elegance to how rovers themselves are designed. They are not simply remote-controlled toy cars sent to another planet. They are mobile laboratories, careful enough to drill, abrade, analyze, image, and sample, but robust enough to survive dust, temperature swings, and years of gradual wear. They must make use of limited power, limited delta rates, and finite mission lifetimes. Commands are planned, transmitted, executed, and reviewed with long delay and no possibility of quick hands-on rescue. A rover drive that looks modest in distance can represent enormous work in planning and hazard evaluation. Mars is explored one cautious wheel turn at a time because there is no mechanic down the road. That sense of care was beautifully complicated by Ingenuity, the small helicopter that flew with perseverance. Ingenuity's purpose began as a technology demonstration, to see whether powered flight could work in Mars's thin atmosphere. The challenge was severe. The air is so sparse that a rotorcraft must spin very fast, operate autonomously, and survive cold nights. And yet Ingenuity flew again and again, turning a demonstration into an aerial scouting partner. It did not replace rovers or orbiters. It added another layer to the conversation between scale and movement on Mars. Orbiters gave the broad map, rovers gave the close reading, and for a while, a tiny helicopter gave local perspective from just above the ground, where navigation and texture begin to meet. Curiosity, down in Gale Crater, represents one mode of knowing. its central question has been whether Mars ever had the right environmental conditions to support small life forms called microbes. Early in its mission, Curiosity found chemical and mineral evidence of past habitable environments. Layer by layer, the rover has explored sediments that record changing lakes, changing chemistry, changing dryness, and changing habitability through time. Gale Crater is compelling because it combines place and sequence. It is not only a location where water once existed, it is a place where the order of environments is stacked in rock, and that makes it possible to read change rather than merely prove occurrence. There is something almost library-like about Gale for that reason. Curiosity can cross from one unit to another, climb through layers, and compare what persisted with what changed. One bed may suggest quiet lake deposition, another may record changing chemistry, changing water availability, or episodes of drying and fracturing. Veins can point to fluids moving through rock after deposition. Grain size can speak to the energy of transport. Sedimentary structures can hint at ancient currents or settling in calm water. A crater that once might have seemed only like an impact scar becomes, under the rover's patient attention, a repository of environmental transitions. Mars stops being a still photograph and becomes a sequence. Perseverance, by contrast, carries a sharper emphasis on biosignatures and samples. It is searching for signs of ancient microbial life and collecting core samples of rock and regolith for possible future return to Earth. Jezero Crater was chosen because it appears to have once held a lake and river delta, exactly the kind of environment where sediments can trap and preserve fine details. Over its first years, the rover explored the geology, water history, and habitable environments of Jezero, collected a diverse set of samples, demonstrated an off-world helicopter, and carried out oxygen production experiments relevant to future human exploration. Perseverance is in some ways the most explicit expression of the modern Mars strategy. Geology, life detection, caching, engineering, and future planning all braided into one mission. Jezero itself is almost a lesson in scientific restraint. A delta is exciting because on Earth, deltas are sediment traps, chemical sorting systems, and environments where fine materials can preserve traces very well. But a delta is not automatically a proof of life, just as a lake is not automatically a cradle of microbes. What Jezero offers is a compelling preservation setting. Sediments washed in from a watershed, entered standing water, settled, were altered, and then remained available for study. That is why the samples matter so much. A tube filled on Mars is not simply a souvenir from a remarkable place. It is a carefully chosen piece of planetary memory, sealed for a later and more exacting conversation on Earth. Before any of those cached samples return, we already possess a few accidental samples of Mars in another form, Martian meteorites. Some rocks blasted off Mars by impacts eventually crossed space and fell to Earth, where scientists identified them through chemistry, trapped gases, and isotopic matches to the Martian atmosphere measured by spacecraft. Meteorites are not perfect stand-ins for hand-selected rover samples. They are biased towards certain rock types and violent ejection histories. Even so, they have mattered enormously. They let researchers date some Martian rocks directly, study igneous histories, compare laboratory analyses with orbital and rover observations, and understand that Mars has been sending fragments of itself into our collections long before we learned how to ask properly. That fact gives the whole sample return idea an almost poetic grounding. Mars has already reached us, but not on its own terms. Meteorites arrive battered, untargeted, and separated from their original field context. What modern exploration seeks is something calmer and more deliberate. not a random fragment from an impact, but a chosen core from a known outcrop, taken from a mapped landscape, documented in images, measured in place, and then brought back with context intact. Context is everything in planetary geology. A rock is useful. A rock with its setting, relationships, mineralogy, and history is vastly more useful. That is why the sample caching effort feels so important. It is the difference between finding a page torn loose and retrieving a page still in the book. The sample return concept is especially powerful because there are limits to what even a brilliant rover can do in place. Instruments on Mars are constrained by size, power, mission lifetime, and the impossibility of endlessly upgrading a machine already on another planet. A carefully selected sample brought back to Earth can be studied by laboratories far more sophisticated than any instrument we can currently land there, and it can be restudied by future generations with tools not yet invented. Sample return is not about retrieving trophies. It is about moving the question of Martian life and planetary history into a laboratory setting where chemistry, isotopes, textures, organics, chronology, and contamination control can all be pushed far beyond rover scale limits. And yet even samples, if they return, will not make Mars simple. That is worth saying softly. Mars tends to attract decisive narratives. Once wet, now dry. Once habitable, now dead. Perhaps alive, perhaps not. But the actual scientific mood is more layered. Early Mars may have had long-standing water supplies in some places and times, while elsewhere it remained cold and dry. Valley networks may imply runoff, while climate models struggle to maintain steady warmth. Northern Ocean hypotheses remain debated. Methane observations have been intriguing but difficult to interpret consistently. Some minerals imply particular water chemistries, others imply transitions away from them. The deepest pleasure of Mars science may be that it resists becoming only one thing. Even the red colour, which seems like the easiest fact in the world, carries a history within it. Mars is the red planet because iron-bearing minerals in its dust and soil oxidized, rusting over immense time. That redness is not just decoration, it is chemistry made visible. It is the look of a surface that interacted with oxygen in minerals, a surface weathered, altered, and broken down into the fine dust that now drifts across plains and paints the sky. A person could spend an entire evening thinking about that alone, a world whose identity, in human language, is the colour of iron after a very long argument with the environment. And then there is the hemispheric dichotomy, which sits under many of these local stories, like an unresolved prologue. Mars has a low-lying northern hemisphere and a higher, more heavily cratered southern one. Explanations have included giant impacts, internal processes, and combinations of both. However it formed, the dichotomy shaped later geology, drainage, volcanism, and probably the distribution of environments over time. Some questions on Mars feel like details. This one feels architectural. Before you ask where the water ran or where the lava spread, you find yourself asking why the floor plan of the whole planet turned out this way. The two small moons deserve a place in the file as well. Phobos and Deimos are tiny, irregular, dark, and oddly humble companions for so dramatic a planet. They may be captured asteroidal bodies or remnants produced by a giant impact and later reassembled in orbit. Their origins are still studied, and either answer would connect them to larger solar system stories about impacts, debris, and orbital evolution. Phobos, the larger and closer of the two, is gradually spiraling inward and will not remain as it is forever. One day, on timescales far beyond us, it may break apart and form a ring or crash into Mars. Even the moons of Mars seem to carry a note of impermanence, If you step back far enough, the full picture becomes strangely elegant. Mars formed as a rocky planet. It differentiated, built crust, generated a magnetic field, suffered intense bombardment, and hosted immense volcanism. It preserved ancient highlands. It recorded water in valleys, deltas, lakes, altered minerals, and perhaps larger northern bodies. It then lost atmosphere, lost warmth, lost its global magnetic shield, and shifted toward a colder, thinner, drier state. Yet it never became geologically meaningless. Wind took over some of the sculpting. Ice kept moving in and out of the story. Volcanoes may have remained locally active far longer than one might guess. Dust storms still walk around the planet. Rovers still roll. Orbiters still circle. Mars is not a fossil exactly. It is more like an old city with active weather and inactive plumbing, where some districts are ancient, some were renovated late, and the archive room is still open. That ongoing exploration is part of why Mars feels so present. We are not merely looking back at a completed chapter from afar. We are, in a limited robotic way, still in the room. Orbiters relay images and measurements home. Mission planners decide where to drive next. Engineers worry about antennas and memory and wheels and dust. Scientists debate deltas and organics and sulfates and fracture fills and sample priorities. It is a very modern way to study an ancient world, by sending patient machines to gather evidence one careful packet at a time across tens and hundreds of millions of kilometers. There is also something worth saying about scale, because Mars can distort it. We hear about a canyon thousands of miles long, a volcano more than 25 miles high, plains and bulges and basins the size of countries, and it all risks turning abstract. But Mars is also intimate at the scale the rovers show us. Pebbles rounded in old streams, fine laminations in sedimentary rock, drill holes, dust on rover decks, cracks, veins, concretions, ripples. A whole planet becomes knowable through a thumbnail image of layered stone. This is one of the gentle lessons Mars teaches. Planetary history is told by grand topography, yes, but also by grains, chemistry, and the patient reading of textures. Olympus Mons tells one truth: a mudstone does too. Mars also becomes more understandable when set beside Earth, not as a failed copy, but as a diverging relative. Both are rocky planets in the inner solar system. Both once had more intense internal heat and heavier bombardment. Both built crust and hosted volcanism. Yet Earth stayed larger, wetter, and more tectonically active. Earth kept a thick atmosphere, stable surface oceans, and a biosphere that altered the planet in return. Mars, smaller and less protected, cooled faster, lost its global field, and saw its atmosphere thin. Water became harder to sustain at the surface. One world remained dynamically inhabited. The other preserved earlier chapters with far less overprinting. The comparison is not a morality tale. It is an exercise in planetary outcomes. That comparison matters beyond our solar system too. When astronomers find rocky exoplanets around other stars, the most immediate questions are often about size, atmosphere, heat, water, and habitability. Mars and Earth offer two nearby examples of how sharply the answers can diverge even within one solar system. A rocky planet near the outer edge of one regime can preserve water or lose it, retain protection or lose it, sustain long-term surface habitability, or retreat into a colder, more hostile state. Mars helps remind us that habitability is not a label stamped at birth. It is a long negotiation among atmosphere, interior heat, chemistry, orbital history, stellar environment, and time. For future humans, Mars remains both horizon and warning. The atmosphere is thin, Radiation is a hazard. Dust is pervasive. Soil chemistry is not automatically friendly to organics or people. Water resources would have to be identified and used carefully. Communication comes with delay. Depending on the orbital positions of Earth and Mars, a message can take many minutes to cross the gap. Even with relay support, Mars is not a place you visit casually. The scientific interest and the engineering challenge are inseparable. The better we understand the planet, the less likely we are to romanticize it into something it is not. Even getting there and arriving safely is its own science. Entry, descent, and landing on Mars is famously difficult because the atmosphere is thick enough to create intense heating and drag, but too thin to make parachutes alone sufficient for large payloads. A spacecraft has to manage hypersonic entry, thermal protection, parachute deployment, guided descent, and final touchdown under conditions that allow little improvisation. The old phrase about Mars is that it is too much atmosphere and not enough atmosphere at the same time. That paradox says a lot about the planet. Mars is often most challenging precisely where it seems simplest. It offers just enough of something to complicate everything. Then there is the matter of staying. Human explorers would need shielding from radiation, reliable habitats, power systems that can endure dust and cold, methods for extracting or transporting water, and systems for making air and fuel or conserving them with extraordinary efficiency. Experiments like oxygen production from Martian carbon dioxide are interesting not because they solve all those problems at once, but because they begin turning the planet from pure obstacle into partial resource. Even so, one should be careful not to slide too quickly into frontier language. Mars does not become easy because a technology demonstration works. It becomes slightly more legible. That is different and more honest. And for all the machinery, the central question remains almost old-fashioned. Not whether Mars is dramatic, it is. Not whether Mars is beautiful, it is in a severe and dusty way. But whether Mars was ever alive, not in fiction, not in wishful thinking. In the narrow and rigorous sense that tiny organisms may once have metabolized, divided, and left traces in water-rich sediments or protected subsurface niches. The search focuses on places where liquid water was once stable, may still exist below the surface, or where hydrothermal environments could have been habitable. That is a modest framing, and therefore a strong one. It does not promise. It directs attention. Life, if it happened, would have needed context. Mars science is the study of that context. I think that is why Mars has such staying power in the imagination of scientists. It is close enough to tempt comparison, different enough to refuse easy analogy, and old enough to keep secrets Earth no longer can. It may tell us about early rocky planets in general. It may help clarify how atmospheres are lost, how volcanism operates without plate tectonics, how water and sediment behave in thin air and low gravity, how climate archives are stored in ice and layered rock, and how habitability can emerge and recede. It may tell us something about our own world's beginning by showing us a surviving cousin that took another path. And it may perhaps tell us whether biology is something that happened once here, or something that can begin wherever chemistry and time are given half a chance. Still, I suspect that the calmest way to think about Mars is not as the next frontier, or the lost Eden, or the red tomb of a failed world. It is simply as a planet that changed. A planet that once had more atmosphere, and then had less. A planet that once had more available surface water, and then had less. A planet whose interior, magnetism, geology, and climate evolved together. A planet whose largest landforms record the consequences of not having Earth-like plate motion. A planet that kept enough of its old surfaces for us to come along much later and ask what happened here. There is humility in that. Mars is not waiting for us to make it mean something. It already means something. Our job is only to read it carefully. The office is quieter now. The lamp still holds its circle of warmth against the dark, and the Mars folder lies open in front of me with more notes than answers, which feels appropriate. Mars is generous with evidence, but selective with conclusions. It gives us valleys without easily yielding a full weather report, minerals without a confession, sediments without a witness, atmosphere loss without a single dramatic farewell. It is the kind of file that teaches patience, the kind that asks you to look twice at the same page, once for what is there and once for what is missing. So at the end of tonight's journey, what do we know? We know Mars is a cold desert world today, with a thin atmosphere, seasons, polar ice, giant volcanoes, canyons, and dust-driven weather. We know its oldest surfaces preserve a record of impacts, volcanism, tectonics, and water-related processes stretching back billions of years. We know early Mars appears to have been wetter, warmer in at least some places or intervals, and more potentially habitable than the surface is now. We know orbiters and rovers have found strong evidence for past habitable environments, and that Perseverance is collecting samples that may one day be studied on Earth in extraordinary detail. We know the atmosphere thinned over time, and missions like MAVEN are helping explain how. And we know the oldest, hardest question remains open. Did life ever arise on Mars? For now, the answer is not in slogans. It is in deltas and clays, in crater floors and mineral maps, in dust and isotopes and cached sample tubes, in a relay network passing images through the dark, in a canyon too large to hold easily in the mind, in a volcano large enough to make Earth seem modest, in an atmosphere slowly interpreted molecule by molecule, and in the discipline of not claiming more than the rocks can support. That is enough for tonight. The Mars file can rest here on the desk, still open, still unfinished, still worth returning to. And now, at last, we can close the case file gently and let the red planet keep its long silence until morning.